sklearn, Gaussian Process, a deep dive. Scikit-learn's Gaussian Process module offers a powerful tool for non-parametric regression, enabling you to model complex relationships between input and output variables without imposing strict assumptions on the underlying data distribution. This module leverages the Gaussian process framework, a probabilistic model that represents functions as random variables drawn from a Gaussian distribution. Here's a detailed breakdown of Gaussian process. Core concepts. Gaussian process. A Gaussian process (GP) is a stochastic process where any finite collection of random variables has a joint Gaussian distribution. This means that the function's values at any set of input points are jointly Gaussian. Kernel function. The kernel function defines the covariance between any 2 points in the input space. It captures the underlying correlation structure of the data, ultimately determining the smoothness and shape of the function. Prior and posterior distributions. A GP prior specifies the distribution of the function before observing any data. After observing data, the prior is updated to a posterior distribution, reflecting the learned relationship between inputs and outputs. Sklearn's implementation. Gaussian process regressor. Gaussian process regressor is the central class within sklearn, Gaussian process. Let's explore its key aspects in detail. Class name: Gaussian process regressor. Description: Implements Gaussian process regression (GPR), a powerful non-parametric model for regression problems. Parameters. Kernel: the heart of the model. It determines the covariance function between input points, influencing the smoothness and shape of the learned function. sklearn, Gaussian process. Kernels offers various kernels like RBF, radial basis function, matern, and linear, allowing you to customize the model's behavior based on your data's characteristics. Type kernel. Required true. Alpha: a regularization parameter that adds a small value to the diagonal of the kernel matrix. This helps to avoid numerical instability and improves the model's robustness. Type float. Default 1e-10. Optimizer controls how the model finds the optimal parameters for the chosen kernel. You can specify a built-in optimizer like FMINLBFGSB or provide your custom optimization function. Type str or callable. Default FMINLBFGSB. N restarts optimizer for optimization. The model starts from multiple random initializations. This parameter determines the number of restarts, aiming to find a more global optimum. Type int. Default 0. Normalize determines whether the target values are normalized before fitting. Normalization can sometimes improve model performance, especially with datasets containing features with vastly different scales. Type bool. Default false. Copix controls whether the input data X is copied before fitting. Setting it to true protects the original data but incurs a performance cost. Type bool. Default true. Random state: the seed used for random number generation. Setting it ensures reproducibility of the results. Type int. Random state instance. Or none. Default none. Methods. Fitx. Y trains the Gaussian process model based on the provided training data X and target values Y. X training data. Type array like of shape N samples. N features. Y target values. Type array like of shape N samples. Or N samples. N targets. Predictix. Returns TD false. Return cov false predicts the target values for the given test data X, along with the standard deviation if returns TD is true and covariance if return cov is true of A. Predictive distribution. X test data. Type array like of shape N samples. N features. Returns TD if true. Return the standard deviation of the predictive distribution. Type bool. Default false. Return cov if true. Return the covariance of the predictive distribution. Type bool. Default false. Score x. Y evaluates the model's performance using the R2 score. X test data. Type array like of shape n samples. N features. Y true values for x. Type array like of shape n samples. Or n samples. N targets. Log marginal likelihood x. Y. Eval gradient false. Clone kernel true calculates the log marginal likelihood of the data under the current model. This provides an indication of how well the model fits the data. You can also optionally calculate the gradient of the log marginal likelihood. Useful for model optimization. X training data. Type array like of shape n samples. N features. Y target values. Type array like of shape n samples. Or n samples. N targets. Eval gradient if true. Calculate the gradient of the log marginal likelihood. Type bool. Default false. Clone kernel if true. Clone the kernel before fitting. Type bool. Default true. Sample x. N samples 1. Random state none generates samples from the Gaussian process model for the given input points x. X points at which to generate samples. Type array like of shape n samples. N features. N samples the number of samples to generate. Type int. Default 1. Random state the seed for random number generation. Type int. Random state instance. Or none. Default none. In summary, sklearn, Gaussian process provides a powerful, flexible framework for non-parametric regression. With Gaussian process regressor, you can model complex relationships between input and output variables, leveraging the expressiveness of Gaussian processes. By carefully choosing the kernel and optimizing its parameters, you can achieve highly accurate and interpretable predictions. Further exploration. Kernels dive deeper into the sklearn, Gaussian process, kernels module to explore the various kernel functions available and learn how to combine them for specific modeling needs. Hyperparameter optimization. Explore techniques for optimizing the kernel's parameters to enhance the model's performance. You can experiment with grid search, random search, or more advanced Bayesian optimization methods. Model evaluation. Familiarize yourself with different metrics for evaluating the performance of Gaussian process regression models, such as R2, mean squared error MSE, and mean absolute error MA. Applications. Explore real-world examples and applications of Gaussian process regression in various domains like machine learning, robotics, finance, and scientific modeling. By understanding these aspects of sklearn, Gaussian process, you gain a solid foundation for applying Gaussian process regression effectively in your own projects.